So today I'd like to introduce Eric Jensen, our speaker. He's a professor of astronomy at Swarthmore College near Philadelphia, where he also teaches about climate change in the environmental studies program. He's especially interested in planet formation in binary systems and whether such planets would ever be habitable. He and I have both worked together on observing transits of exoplanets through the KELT program, in my KELT shirt, Kilo Degree Extremely Little Telescope, where he wrote the online transit finder software, which is very useful. Thank you very much, Eric. So tell us about these binary systems.
Okay, so let me share my screen here. So first, I'm excited to be here. It's nice to see everybody virtually and to get a chance to talk about this. So let me pull this up and we will jump right in. Okay. So what I want to talk to you about today is a question that I've been interested in for a while, and I have been interested in it probably for about 20 years in the context of binary stars themselves. But recently, I would say in the last 5 years or so, it's really intersected in an interesting way, I think, with exoplanets. So our story today is going to have two parts where we first talk about some interesting things about some exoplanetary systems. And then I'll tell you a little bit about some current work that I'm doing about something that might be an explanation for that, or at least a partial explanation for that. And I'll say that I'm happy to keep this relatively informal. If there are questions that people have as we're going along, I know it's a little hard on Zoom, but if people want to just jump in and ask a question. So especially if you see something on a particular slide that you want to have clarified or something that I just said, if it's relevant in the moment, feel free to just jump in and ask that question. Of course, I'll also be happy at the end to take questions that you have then. So we can do either one of those, and we'll just see how that goes. Okay, so the very first thing that I want to do is a little bit different, and that's a little bit of audience participation. So I'm going to shift so I can see more people here. And so what I want you to do, this is a little odd, but bear with me, is point to where the nearest grocery store is, or the grocery store that you usually shop at. So for me, that would be like back there somewhere. Okay, so I see some people pointing right at the screen. I see there's two people that don't agree with each other who are sitting next to each other on the couch. They're pointing behind. I see. I thought they were both pointing at each other. Okay, so I'm seeing various people pointing different places, but I'm not seeing anybody point up, and I'm not seeing anybody point down. And that's not surprising, right? Because, we're on a curved Earth, but to a first approximation, the part of the Earth that we deal with on an everyday basis is pretty flat. And when we're on a flat surface, or we're sort of inside a flat distribution of things, the direction to everything of interest is a circle that goes all the way around us. And the reason that I bring that up is that that's actually what we see in our solar system. So our solar system is pretty flat. And the way that we can tell that is when we look up in the sky, we don't see planets in just any direction. There's a particular line across the sky where we always see the planets. And here's a pretty amazing picture. It's really a composite picture. I'm going to make the labels a little bit bigger. So this was on Astronomy Picture of the Day a couple of years ago. And this is actually a composite of an image that was taken of the western horizon a bit after sunset for part of the sky, and then later of the eastern horizon before sunrise, and then stitched together. So you're actually looking at the whole pretty much 360 degrees of the sky from here to here, with the sun just below the horizon in either direction. And what you see is Mercury, Saturn, Jupiter, Uranus, Venus, Mars, Neptune, and the sun just below the horizon. And actually the moon is right there as well. And they're all on a nice straight line. And that's because the arrangement of our solar system is pretty flat. If we zoom in a little bit here, you can see the planets a little bit better. So this is looking over towards one horizon. There's Mercury, there's Saturn, Jupiter. Of course, there's other things along this line, like Antares in the constellation of Scorpius, the red star there. If we zoom over to the other horizon, Neptune is sort of pulled out here because you would never be able to see it. Otherwise, Uranus, you can just barely see, but we get Mars and Venus here. So all on this nice line. I'll point one thing out, actually, that's a little bit of an aside here, but that you can see nicely in this picture. If you look at Mars right here, nice red dot. And then if I go back to the previous slide and you look at Antares, they look very similar and they're both very near the ecliptic. And in fact, this name, some of you may know, this name Antares, that ant is like anti, that means not Mars. The Greek god, Roman god Ares, god of war, is the same as Mars. And so that name Antares actually is a little reminder that maybe that red thing that you're looking at on the ecliptic isn't Mars after all. Okay, so we've got a pretty flat solar system that we're sitting inside of. So we see the planets spread across the sky like that. It turns out the sun actually participates in this as well, not just in sitting in that same plane. Of course it does, because all the planets orbit around the sun. But I want to point out that the rotation of the sun is related to this as well. So here's a movie made in New Jersey, Big Bear Solar Observatory, of the sun over many months here. The sun takes about a full month to rotate once on its axis. So if you look at the dates here, you can see a bunch of months going by there. And so with the sun's rotation, we can actually, just like we do for the Earth, we could define an equator for the sun. So we could draw a line there across the sun that it's a rotational equator. And it turns out if we take that equator, and then we also look at where the orbits of the planets are, I'll add them here. There's the orbit of Mercury, there's Venus, there's Earth, there's Mars. They are also in about that same plane. So that flat plane of the solar system is not just the plane that the planets lie in, but that's also the plane that the sun rotates in. So those different motions on very different scales, all the way out to Jupiter or Saturn going around, you could think of the axis that they're rotating around. The axis that all the planets are orbiting around, perpendicular to its orbit, is the same axis, more or less, that the sun's rotating around. So those different motions are lined up with each other. I don't have Jupiter and Saturn and Uranus and Neptune on this plot just because it was getting a little bit busy, but if I did, they would be about the same as well. Actually, all the other, if we took the sun and Mercury out, most of the other planets are actually lined up with each other even better than that 5 or 6 degrees. The sun's maybe 6 degrees off. The rest of them are within just a degree or two of each other. But all that's, that's a little bit in the details. It's all very close. It's all pretty flat. We kind of take this for granted, but we'll see in a little bit that it wouldn't have to be that way. And we have a very natural explanation for this, in fact, which is that we think that the way the solar system formed was that before there were planets there, right after the sun formed, there was a big orbiting flattened disk of gas and dust, like you can see in this artist's conception, or over my shoulder in the artist's conception there, of what we call protoplanetary disks. So these are big conglomerations of gas and dust. We see them around young stars. I'll show you real images and not just artist images in a minute. But we think that the reason the planets are in a flat plane today is that they formed originally from a flat orbiting disk of gas and dust. And so they're maintaining their sort of primordial geometry that they had. So this was an artist's conception. This is actually a real image. The very first time I saw it, I was like, oh, that's a nice artist's conception of that disk. I wonder what the images really look like. There's a new set of radio telescopes, relatively new now, about maybe been in service 7 or 8 years, called ALMA in Chile, the Atacama Large Millimeter Array. And it can take amazing images now of these flattened disks of gas and dust. So this is a star called HL Tau. It's about 500 light years away from Earth, only about 1,000,000 years old. Since you are all interested in astronomy, maybe you won't laugh when I say only 1,000,000 years old. That's young on astronomical timescales. And what we're seeing here, this is light that your eyes wouldn't be able to see. This is at wavelengths of about 1 millimeter in the radio, or what sometimes called the microwave part of the electromagnetic spectrum. And this is gas and dust that will, what I was going to say will eventually form planets, because we used to think 1,000,000 years was too long. But one of the things that Alma has seen, and you can see it very clearly in this image, is these rings here. We think actually there may already be planets in this disk, and they've cleared out those gaps in the disk. And so even at 1,000,000 years after a star forms, there may be planets forming around it already. That was sort of the first image of this quality of one of these young disks. Since then, we've had many more. So these are all also real images. The colors here are just chosen to highlight different scales. Again, your eyes can't see this light. And so what we choose to color it in an image is a little arbitrary. But all of these are disks around young stars. A bunch of them show that structure gaps. Some of them even spiral arms. In the top middle here, you can see maybe some spiral arm structure. Kind of in the lower right here is one with a couple nice spiral arms. And the reason that some of them have a little bit different shape is just that they're tilted more. So we think all of them are circular if they were face on to Earth. But if you take that circle and you tilt it, then you get more of an oval shape here. This one's in a binary system. Yeah, did somebody have a question?
Eric, I believe someone had a question. I saw a hand up.
Yeah, I had a question. In the slide before, you showed us the picture by ALMA. I think the satellite is called ALMA. Yep. How do we know that it's a star system that's at about 1,000,000 years old? That's 500 light years. I know how we can tell how far it is, but how can we tell how old?
Yeah, so how can we figure out how old it is? That's basically from so getting ages of stars is a challenging thing, and that's the way we get ages of planets too. It's basically from detailed calculations of how long it would take a star that collapses to reach a certain brightness and temperature. So we see stars of different ages follow a clear evolutionary path where as they're collapsing, they get hotter and they get somewhat more luminous as well. And so that's one of the ways. So it's really theoretical calculations that are calibrated that give us that sense of it. But it's a challenging thing to try to figure out. The only, so on Earth, we can do like radioactive dating for things in our own solar system. For things outside the solar system, we pretty much rely on theoretical models. Okay, so here's a bunch of disk images. So thanks for that question. And these disks, so here they're mostly face on, and I mentioned solar systems being flat. This is a bunch of disk images from a group that went out and tried to find the ones that were the most edge on possible. And you can see that these things are really skinny. So these forming solar systems, in this case, we're looking at them edge on, are really pretty flat. And so our solar system today, we think, is flat because it started out flat before it formed. Okay. So this is a little bit of a leading question because you saw my title and you can maybe see something in the background here. So we had thought for a long time. So before we discovered planets outside the solar system, we kind of assumed that every solar system would be like ours. That has turned out to be true in some ways, but not true in some other sort of interesting ways. And so let's ask this question: are other solar systems this flat or not? And then, of course, that raises the question: well, how do you know? How are we going to do it? So I'm going to talk through how we can try to figure this out. So the first way that you might think of trying to figure this out is if we could just take a picture of another solar system, then that would tell us right away. And so what you're looking at here is in fact a picture of another solar system. So there are 4 dots in this picture that are actually planets orbiting the star. So there's one up here, there's one right there, there's one right there, and then there's this close-in one right here. And what you're looking at here is where the star would be if its light wasn't blocked out. So the challenge with taking pictures of planets as a way to detect them is that it's not so much that the planets are too faint, it's that the star is too bright, that you have these faint things next to this really bright thing. So like somebody's shining this bright spotlight right in your face and then trying to ask you to see a little firefly in the background or something. You could see the firefly fine if the spotlight wasn't there, but with that bright light there, it's hard to do. So the game here, or the challenge here, is to try to block out the starlight the best you can. And here is an amazing to me movie taken over a period of years of these planets orbiting around this star. And so now we can tell much more clearly that this inner blob here is really a planet. The stuff you see in the middle here are speckles from not being able to quite perfectly subtract the light of the star. But we can see very clearly that all these things are orbiting around the star. And it turns out that if you map out those orbits, or those parts of orbits that we can follow, that this is consistent with all of those things being in a flat distribution. It's again, a flat solar system, but in this case, one that we're looking at pretty face on. Okay, so this makes it look easy. Like we'll just be able to look at a bunch of solar systems and we're able to tell if they're flat or not. But as I mentioned, it's challenging to take images of planets, and it turns out that the number of solar systems for which we can make a movie like this is 1. So this is really the only system where we have data that are this good. There's a handful of other systems, really maybe like 2 hands full, like 10 systems where planets have been directly imaged like this. In most cases, just like 1 planet per system. Maybe we've seen a little bit of orbital motion of it, but it's a really hard thing to do. Mainly because the distance for most stars, the distance at which we can block out the light well enough kind of encompasses the whole solar system. It's hard to get close enough into the star there to see it. These planets are really far out from their star. Okay, so for this one, it's flat, but it turns out this technique isn't going to work for us to try to study a bunch of solar systems. Okay, so what else do we do? The way that by far the majority of planets we know about around other stars have been found is by using what are called transits. So of the more than 4,000 planets we know about, 90% of those probably have been found with this transit method. So let me take many of you may be familiar with it, but let me take a few minutes to explain it. So this is a picture of our own sun taken back in 2012. And that black dot right there is the planet Venus that underwent what was called a transit, so-called transit of Venus transiting or moving across the face of the sun. There was one of those in 2004 and one of those in 2012. Did any of you happen to see either of those transits of Venus? Okay, some people are saying yes. And that's good because there's not going to be another one for 100 years. It's sort of a quirk of our solar system that as flat as it is, that couple of degrees of difference in our orbit and Venus's orbit means that it's very rare that we can see a transit of Venus. Transits of Mercury are a little bit more common. Okay. But we can use this idea that if a planet goes in front of a star, that it blocks a little bit of the star's light to actually detect planets around other stars. So here's a cartoon, and what's showing on the top is what's actually happening, and what's showing on the bottom is the thing that we can measure. So we can't take a picture of most stars and see the planets separate from them, but what we can do is measure the brightness of the star very precisely. So as the planet moves across the star, what we see on this bottom graph here is brightness plotted on the y-axis and time plotted on the x-axis. And during the time when the planet is going across the star, it blocks a little bit of the star's light, so the star gets a little bit fainter. And this graph here is maybe a little bit misleading because it doesn't go anywhere near all the way down to 0. Planets are small compared to stars for the most part. And so a planet the size of Jupiter, I know I'm going like this because that's nothing like what the size of Jupiter is, but maybe relative to the star. A planet the size of Jupiter and a star the size of the sun, Jupiter is about 1% of the cross-sectional area of the sun. So it blocks about 1% of the star's light. And so one of the cool things about this technique is if we see this dimming, not only can we tell that there's a planet there, but we can tell how big the planet is compared to how big the star is. Just the area, pi r squared for the planet divided by pi r squared for the star gives you the amount of dimming that you get. Or put it the other way around, we measure the amount of dimming, we infer the radius of the star from other measurements, and then we can get the radius of the planet. So this is a way to detect planets around other stars. But I just said to you that we can't see the picture at the top. We can only see the brightness data at the bottom. So how are we going to use this to get the information we want about how the orbit might or might not be tilted? Well, one thing that we can do is look at systems where there are multiple planets. So again, you probably don't need me to tell you that these are not real images of planets. This is an artist's conception of this system around a nearby star called TRAPPIST-1. And it turns out that all 7 of these planets are lined up such that they pass in front of the star. So here's what the real data look like. So this is a graph, again, of brightness on the y-axis, of time on the x-axis. And you can see in these measurements for 7 different planets that they transit in front of the star. And to have a 7-planet system where all of the planets, as we see them from Earth, pass in front of the star, they have got to really be very well aligned with each other. So for this system anyway, we can tell that that the system is pretty flat. And one of the things you can see here, again, just a little bit of an aside, you can see as we go from top to bottom that these transits, these dips are wider and wider. And that's simply because as you go farther away from a star, the planets move more slowly. So the Earth takes longer to go around the sun than Mercury does. The Earth moves more slowly than Mercury. And so as we look at it from a distance, the close-in planets go across the star pretty quickly, and the planets that are farther out go across a little bit more slowly. Okay, so here's a case of a pretty flat solar system. And there are a bunch of these systems where there are we see multiple planets that transit the star. So this is just a subset of them from what was called the Kepler mission. And these are systems where there's at least 4 planets in the system. And I didn't even try to fit the whole figure on here. There's maybe twice this many or something. But again, all these would have to be pretty flat for the planets to transit the star. Again, as an aside, I'll point out one thing here that I think is kind of cool. So this says the type is a little bit small. This says Sol. So this is our solar system for comparison with the 4 inner planets. So that's Mercury, Venus, Earth, and Mars there. And one of the things that's striking to me about all the extrasolar planetary systems is I used to think of Mercury as very close to the sun. And at some level it is. It's the closest planet we have to the sun. But when we look at other solar systems, one of the things we find is that almost every solar system we look at has a planet closer to its star than Mercury is. And a bunch of these, some of these have like 5 planets closer to the star than Mercury is to our sun. They're just really, really packed in there. Okay, so some solar systems for sure are flat. But now I'm going to tell you about some weirdos. And I'm going to show you, so here's some not so great data, but it still shows the effect that we're looking for. I included this because it's from our own telescope at Swarthmore. So again, this is time, this is brightness. We see, some points kind of clustered up here, and then it gets fainter, and then it comes back up. So on the right-hand side and the left-hand side, it's a little bit brighter, and in the middle, it's a little bit fainter. And here you can actually really see the scale. You can see that this dip is maybe only about 0.5% of the brightness of the light overall. And the reason I picked this particular graph here is that this was in the CELT survey that Mary Lou was also part of. And this designation KC11C043952, this planet candidate that we have eventually turned out to be a real planet. It was the 9th discovery or confirmed planet that we had with the survey, and it turned out to be really interesting and eventually turned into this publication. This is still to date the hottest known planet around any star. And it's for two reasons. One is that the star that it orbits is a really hot star. And second, that the planet itself is very close to the star. So much closer than Mercury is to the star. And the star itself is maybe 2 or 3 times as hot as our sun. And so the temperature of the planet is 4,600 degrees Kelvin. To give you some comparison, the sun is 5,800. So this is not too much cooler than our sun, and it's a planet. It's just sitting there right next to the star. But the extreme nature of the temperature of the planet isn't so much why I'm interested in it for our story, but it's the orbit. So here is an animation that was produced as part of the press release for this planet discovery. And there's 2 interesting things going on here. One that catches your eye first probably is this big tail of gas. So the planet's so hot that it's getting kind of cooked by the star and it's losing mass there. But there's another weird thing about this animation, and that's the rotation of the star. So if I do the same thing, but I turn it on its side, you can see the star is rotating like this, but the planet is going around like that. So this was our sun, and with the other planets in the solar system in this plane, this would be going over the North Pole and the South Pole of the sun. Instead of our planets that are a few degrees from the sun's equator, this planet is 85 degrees from the star's equator. Okay, it's fine to claim that from an animation that I just showed you, but how in the world do we know that? We can't see the star rotate, right? We can't see the planet orbiting. And so how do we know how they're oriented relative to each other? So that's what I'm going to tell you next. It takes a little bit of buildup, but we'll get there. It's really part of astronomy is trying to people being clever, not me, but other people being clever and figuring out ways to use light, because that's all we have as astronomers, and pull out information that's hidden in there. And in this case, information about positions of things that we can't actually see. Okay, so remember, here's our image of the rotating sun. And we need to take advantage of something called the Doppler shift. So some of you may have heard this. Certainly all of you have experienced it in terms of sound. And so this is the idea that when things move, then the wavelength of light or the wavelength of sound that they emit gets shifted by their motion. So you hear it every day if you stand by a busy road, or you live on a busy street here, and if I hear a car go by, it goes shifts from a little bit higher pitched to when it's coming towards us to a little bit lower pitched when it's going by. And that's because as the object's moving, it's sort of keeping up with each successive wave crest that it emitted before, so they kind of get squished together when it's coming towards you. And when it's moving away, it's a little farther away each time it emits a crest of the wave. So we get those a little bit more spread out. We can hear that for sound because the speed of sound is not so much greater than the speeds of everyday objects we see. We never see it directly for light because the speed of light is so fast, but it happens for light as well. So if an object is moving towards us, the light gets shifted to slightly shorter wavelengths, or blue shift. It's moving away from us. It gets shifted to slightly longer wavelengths. So you would never see an image like I've drawn here with your eye from a rotating star. You need to have precise instruments to measure it, but it can be measured. So if in this image, the left-hand part of the star is rotating towards us, so its light's a little blue shifted, the right-hand part is moving away. Okay, so what do we do with that? Whoops, went the wrong way. Okay, so what we can do with that is, remember the planet is moving across the star. And so when the planet transits, it is going to first go across the blue limb of the star here, and then it's going to go across the red limb of the star. And if we can measure during the transit those different wavelengths of light very precisely, and we can look at what's called a spectral line. So different elements emit light at very precise wavelengths, but those could get shifted a little bit blue or a little bit red. And the slightly bluer light or the slightly redder light we see is actually coming from different parts of the star. So there we're getting some information about position from the wavelength of the light, whether it was coming from the blue side of the star or the red side of the star. Here's some real data showing on the top a spectrum of a star that's rotating quickly, and on the bottom of a spectrum of a star that's rotating slowly. So all stars have these dips in their spectrum. We call them spectral lines that come from transitions of particular elements. And here we've got some iron, we've got some nitrogen, we've got some manganese, I guess. And the thing that you can see is in a slowly rotating star, that's at a pretty narrow range of wavelengths. But that narrow range of wavelengths, if the star is rotating quickly, gets spread out to a wider range of wavelengths. The same wavelength of light gets red shifted from one side of the star, it gets blue shifted from the other side of the star, so the whole thing gets spread out a bit. So we can actually, this is how we measure the rotation of stars. But here we're going to use it in conjunction with transits to figure out how the planet's going. So now let's combine these two animations. So as the planet is going across, it first goes across the blue limb of the star, then it goes across the middle, which is not moving towards or away from us at all. Then it goes across the right. So if we can carefully measure one of these spectral lines and repeatedly do it while the transit is happening, we can see this little bump on the line that moves across the line that tells us what part of the star the planet is covering at that time. Takes very detailed measurements, but it can be done, and it tells you how the planet is moving. Okay, so the image that I've shown you so far assumes that the way that the star is rotating and the way that the planet is moving is the same. But it might be, if we look at the middle here, that the planet could be going the other way. And then we would see the opposite behavior in the bump in the spectrum. It would go from the red side towards the blue side. Or finally, more like Kelt 9, if it's going straight across here, it hardly moves from red to blue at all. It mostly just sits in the middle of the line here. So by making these careful measurements, we can figure out how is the orbit of the planet oriented compared to how the star is rotating. And it turns out we see all in real data, we see all of these different behaviors. This is a little bit of an overwhelming diagram with a whole lot going on at once, but all of these represent real discoveries, real planets around real stars from the Kelt survey. Some of them are aligned nicely with the star's equator, just like we would expect. Some of them are aligned with the equator, but going the opposite direction. And some of them are kind of going up and over the pole. So there's some planets that are nicely lined up, and there's some that are tilted at weird angles around their stars. And this is one of the big surprises of planets around other stars, that not everything is kind of neat and orderly like it is in our solar system. Okay, maybe I'll pause there for a second, see if anybody has questions about this, because that's kind of a lot of build up to that technique. Anybody want to jump in with a question? Okay, so let's go on ahead.
Hey, if you
Yeah, go ahead.
If you go back real quick.
Yep.
If you look at the graphs of Kelt 17 and Kelt 13, the graphs look almost the same. How can you differentiate how the planet is orbiting. For Cal 17, it looks like it's going like almost vertically. So,
right?
and then for Cal 13, it looks like it's just going horizontally with a little bit of angle. But the graphs look the same almost.
So the graphs, the sort of steady state shape of the graphs look the same, but if we look closely at this one, you'll see it goes from red to blue here, but it never gets to the real extremes of the red and blue. So that's telling us that it's going across right to left, but that it's maybe not cutting all the way across the middle. It's kind of going across the bottom, but you do see a little bump move across here. Here we've got a similar kind of bump, but it mostly just sits on the blue side of the line there. It never really affects the red side of the line. It's subtle, and it's hard to look at these sort of in real time. And the astronomers can like stare at it for a long time. And believe me, it's not quick and easy to. You don't get a little movie like this from the real data, but you get something that's equivalent to it. But then you have time to sort of sort it out, and also let a computer try a bunch of different things and figure out which is the best. Yeah, so I agree. They're not super different, but they're a bit different, and it's how much red versus blue that bump covers. Okay, yeah, go ahead. I can't tell your name, but go. I see you raising your hand.
I could understand the general tendency of the rotation of the planet in the plane of the solar system to be lined up with one another, but it's hard to imagine how it could get to be different from that, apart from some kind of catastrophic interaction that literally tilts the star over. How do you do this?
That's exactly where we're headed next. So I'm glad you asked that question. So that's part two, and part two will not be as long as part one. I know we're not going to keep you here for all night, but yeah. So the big question is why, right? How do you get that? Especially because we have this very nice physical model of these nice flat disks that should form flat solar systems. And indeed, we think that's right. That we think that at the time of formation, that planetary systems are flat. And then, as you say, something has to happen to change that. So the question is, what can change that? Okay, so why do you get these tilted orbits? And I'll say up front, we don't know for sure. This is still very much an active question that we're trying to work out, but there's some leading ideas. I'm going to talk to you about one of those. And it turns out that one of the main ideas that could well be at play here is there are a lot of stars in the sky. There's many, and many of them are in what are called binary systems. So what I've drawn for you just as a cartoon here is a Jupiter-sized planet orbiting a star. And then more distant from that is another star in the system. So our sun is a single star, does not have any nearby, doesn't have any stars that are bound to it gravitationally and orbiting around it. But if you look up at the points of light in the sky, more than half of those individual stars you see are actually pairs of stars, or actually binary systems. And so if you have another star in the system, that can exert a pull on the orbit, or more accurately, a torque to try to twist its orientation that can move the planet. And so the gentleman who asked the question said, well, maybe we're tipping the star over. Turns out it's easier to tip the planet than it is to tip the star. So it's probably what's happening is that the rotation axis of the star isn't necessarily changing, but the orbital plane of the planet is the thing that's getting changed. And so, so if you have a distant star orbiting, it can tip this orbit to try to bring the orbit of the planet into alignment with the distant orbit of the star, but probably not change this star's rotation axis very much. But it turns out this can only happen if the plane of this orbit here and the plane of this star's orbit are tilted relative to each other. If everything starts out all in the same plane, and if it's all nice and flat to start with, it'll just stay nice and flat. So a distant star, if you had a solar system here, and if you had a solar system here, and they're all lined up, that distant star isn't going to really do anything. It's not going to make the orbit of the planet shift. So the question is, so here's a theoretical idea for, do the right conditions exist to make this happen? And that's a question that I've been working on. So the question really, so here's a cartoon version, is when we have two stars, so here you could imagine these stars orbiting each other, each with its own planetary system. When we have two stars orbited by planets, are the orbits of the planets lined up with the orbits of the stars? Maybe systems would form that way in the first place. Or are the orbits of the planets around one star tipped compared to the orbits of the planets around the other star, and also compared to the orbit of the overall binary? Okay, so in this cartoon, we can see the answer, but I told you already that it's hard to see the planets, right? So we're trying to answer this question without being able to see the orbits of the planets, because an orbit isn't a real thing, right? There's no line on the sky that shows you where the orbit is. And also, in fact, we can't see the planets either. So, so we're trying to answer this question by comparing two different things, neither of which we can actually see very easily. So that's a great question for an astronomer to work on. It's like two invisible things, and we want to know how they're lined up relative to each other. Turns out it's not impossible. And so one way to try to tackle this is to think about this idea that I just said of an orbit isn't really a physical object. And here's a picture that's helpful to me to think about this. Not obvious, I'm sure, how this is related. Here's a bunch of people standing in line to vote. What I just said about an orbit is also really true about a line, right? This line of people, absent the people who are standing in it, isn't something that would be obvious. Maybe you could see their footprints in the dirt later, but if this was a concrete surface and the people all go away, or say there was only one person who had to follow this path, you couldn't go back and see what the path was, where the path the person was going to follow or where they have followed it. So that's sort of like, so an orbit with one planet in it, we can only see the planet at one instant in time. And if we can't follow it all the way around, we can't see where it was before or after. But if you have a line or an orbit that's full of people, you can see where the orbit is. And that brings us kind of back full circle to these disks. So after the planets have formed and all the gas and dust has gone away, it's hard to tell where the orbit of the planet is. But all this orbiting material in the disk is completely filling any one given circular path. And so we can tell where the orbits of the planets are going to be and how they're oriented by looking at the position of the disk. And so we can see here that any planets in this gap would have an orbit that's tilted like that. And in particular, if we had two of these systems that both have disks, then we could see whether those two disks are aligned with each other or whether they're tilted relative to each other. And therefore, after the planets form, whether the planetary systems would be aligned with each other or not. And so I mentioned ALMA earlier. Here's a picture of the ALMA set of telescopes. It's quite an amazing facility. Each of these telescopes is 14 meters in diameter. There are 50 of them on this high plain in northern Chile. Here they're in a very compact configuration, but they can be spread out as far as 10 kilometers, six miles apart from each other, which it turns out increases their ability to see fine detail. So what I've been doing is using these telescopes to map some of these disks and disks in binary systems in particular. So here's one particular system that I've studied. So this is a pair of stars. For the northern star, you see this bright starlight here. For the southern star, this is an image taken with the Hubble Space Telescope. For the southern star, it turns out the disk is almost completely edge on, so it's blocking some of the star's light. So even in visible light, we can see that the disk is there. But here you just have the glare of the star. It's sort of like the problem trying to see planets. With the glare of the star, you can't really see the disk very well. but we mapped this system with ALMA, and this is what we found. So what I'm showing you here that's color-coded in red and blue is the orbiting disk of gas and dust, and it's color-coded by this Doppler shift. So this red side of the disk is moving away from us, this blue side is moving towards us, and we can now see very clearly from the rotation of the disks that they're not aligned with each other at all. And so this is the system actually that's in my background here as well, just kind of turned on its side. And this is some work that I did with my longtime collaborator, Rachel Akeson, who's at Caltech, is mapping these out. And this was one of the first really clear images to see this difference in orientation in a binary system of these two planet-forming disks. So the thing that I'll emphasize is that planets will form in this disk, almost certainly, and planets will almost certainly form in this northern disk as well. And those two planetary systems will not be aligned with each other to start. And the distant star will pull on those planets and could, even if the planets start out aligned with their star's equator, over time, it could tilt the planets in their orbit and bring about one of these sort of misaligned systems. So the conditions exist at the time that planets are forming in at least some systems to be able to torque these disks around. It was kind of fun when we published this. So these are just showing the rotation axis of the disks. And here is the artist's conception on the right compared to the data on the left.
So the concentric line. So the concentric lines are just there to illustrate the plane, rather than.
Yeah, that's so right here. These contours. Yeah, so those are showing the sort of relative brightness levels, just like you might on a topographic map that would show elevation. It's sort of showing you how the brightness is distributed in the disk. It's one way to show.
The tighter they are, the greater the difference.
The sort of steeper the change in difference. That's right. And the more levels you go past, then the brighter you are in the center. So the northern one is a bit brighter, in fact, than the southern one.
Thank you.
Like isograds, I think.
I'm sorry?
It like isotherms or isograds.
Yeah, exactly. Right. So it's iso brightness contours in this case. Yep, exactly. So when we published this paper, and there was actually a press release about it, one of the fun things was it kind of got picked up by different news outlets. And so here's one story that I saved a screenshot of that says, this is probably the weirdest binary star system ever discovered. And I especially saved the screenshot for what else I was sharing the screen with. So I was for one brief moment, a story about our astronomy work and a story about legalization of marijuana and a review of Sharknado 2. We're all on the same page. So I got to have that honor might not be the right word, but interesting media experience. The other thing that I think is sort of interesting about this headline, I mean, I understand why they wrote this headline, but I think probably a more accurate astronomical headline now, from what we now know, would be, this binary system is completely normal. So it was the first one we found where we could clearly say what the case was, but it seems like this may be more the norm than the exception, that this may just be how binary systems form. That doesn't make for a very good headline, though, I think. It's like, news today, nothing happened. Okay, we're working on this. I'm currently in the process of working on this to try to see really whether it's weird or typical. I think it may be typical. Here's some similar data. Here's another system. This one is pretty faint, but we can still see the red and blue shift. This system actually is somewhat more aligned with each other, though still a little bit of a tilt there, maybe 20 degrees different. Here's one that's really differently aligned with each other. Again, a pretty faint companion and a brighter one here, but it's looking like this is probably just the way binaries form. and their planetary systems form. And so that may be at least part of the explanation for why some of these planets have weird tilted orbits. Now, I would be remiss if I didn't tell you that not every star has a binary companion. And in particular, not every star where we've detected one of these weird tilted orbits has a binary companion. So this explanation that I've given to you may well be the explanation for some of the weird tilted planets, but it probably isn't the only explanation. And so it's still an active research question of what exactly is going on in all these systems. Maybe there used to be a binary companion that got scattered away somehow. I find that kind of unappealing as an explanation, because you have to invoke kind of not magic, but a special event to make that go away. Maybe but the other leading explanation perhaps is that planets themselves influence each other. Maybe if you have a couple of big Jupiter mass planets in the system and you get a scattering event, a close encounter between one of those, maybe that can kick one into a weird orbit. So maybe it's the planets themselves pushing on each other in the system. To be continued, I think, but this is an open and interesting question right now in astronomy and in planet formation. We know for sure that some planets have these highly tilted orbits. Some of that could be explained by binary star companions, but there's still work to do to figure out the rest of what may be going on. So I'll stop there. Thank you for the chance to talk to you about this, and I would be happy to answer some more questions if you have them.
Great.
I have a quick question, if I could go first.
Okay.
Does anyone want to go before me? Actually, I might be interrupting someone. I think
That's okay. Go ahead. That's fine.
Okay, I was gonna say, what if the whole data we're collecting is just wrong? I like to think like this. I don't want to be like a non-believer, but I love thinking like this. What if let's say there's a star we're watching with the telescope really far away, and then all of a sudden, like let's say a meteor or an asteroid just passes over it, and it looks like a planet orbiting it, but it's actually just some distant object that transits it that's not really in the star system. What if that's corrupting our data? Could that be possible?
So it's certainly possible. So it's good to ask questions about how sure we are about what we know and what the evidence is for what we know. Certainly possible for you to get things that turn out not to be right. So like on this KELP project that looked for transits that Mary Lou and I worked on, in the initial data, we would have a whole bunch of candidates where there would be, in the initial data were sometimes a little noisy, and you would see events and we think, okay, maybe that's a planet, maybe it's not. So then the answer is you go back and look again, you make more observations. And so to take the case that you had, if you just had one transient event and then it never repeated itself, then you'd say, okay, that's not a planet. The thing about these transits, and I only showed you just individual cases, the thing about them is we see them repeat time after time after time. So once you see two events happen, then you have a prediction that said, okay, these two things happened, I don't know what, a day and a half apart. That means a day and a half later and a day and a half after that, and a whole bunch of other times that you could predict, we should see it again. And so then you go check to see if you see it again. If you don't, and sometimes you don't, then that means it was something spurious in your data. But if you do and you see it repeat, then you know it's something that's really there. So you always try to have some kind of checks, and you try to confirm, have independent confirmation of what you're trying to look for. Okay,
So,
other questions?
Yeah. Have you been able, or have they been able to image star clusters, open clusters? I mean, globulars may be too tight, but do you, with more stars interacting with each other closely, how much more likely are we to see these strange orbits that are, perpendicular to the star's orbiting axis?
Right. So the question you're asking essentially, are the tilted orbits more common in environments where the stars are more crowded together?
Right. They can interfere with each other.
In the globular clusters, which are these really dense clusters of stars, people have looked for planets and basically haven't found planets. So it may be that those clusters are so dense, not only that you tilt the planets, but that you lose the planets altogether. And those globular clusters are pretty old too, so you've got a lot of time for that to happen. The open clusters, like the Pleiades, for example, which aren't as dense, I don't think we know of a whole lot of planets that are in clusters. I don't think we have enough data to answer your question, I think, is the the short answer to my long lead up to it. That would be a really interesting question, and it would be consistent with this hypothesis, right? That perturbation from outside things could tilt planets more. We just don't have the data yet, I think, to answer that question, but it's a good idea. Yeah, go ahead. I can't tell who's who, so feel free to jump in.
I have a question. In my kind of naive impression about how clouds of gas and dust condense to form solar systems is that they basically have to get rid of angular momentum so they can continue collapsing, and that formation of a planetary system is one way of doing that, and forming a binary star or multiple star system is another way of doing that. But all of those things ought to make things relatively coplanar. I would imagine that the binary star systems would tend to have rotation axes aligned with the plane of their orbits. And it appears that that's not the case at all.
Yeah, so it's a great question, and that's one of the things. That's what got me interested in this in the first place. Is what can this tell us about binary formation? And so the current picture that's backed up both by these observations, but also by some simulations of formation is that star formation. So star formation and planet formation happen together. You have this collapsing cloud of gas and dust. The dense central part of it becomes the star. The material that's rotating a bit faster falls onto this rotating disk around it. But what's probably really happening is you have a whole bunch of these things happening at once. So you have a big cloud that's breaking into these different fragments, and some of those are staying bound to each other and forming their own stars and planetary systems. And what probably appears to be happening, and seems to happen in simulations as well, is that fragmentation happens early enough that the two little parts of it might be bound together to orbit each other, but each have their own orientation. So you kind of break things apart early on when they're still pretty disordered, and then the individual solar systems sort of evolve from there, rather than having this kind of coherent collapse all the way down and then kind of splitting apart into two more towards the end, if that makes sense. So it's kind of a messy process that's probably forming a lot of stars at once and forming binaries that seem to be misaligned with each other.
Eric?
Yeah.
In the system you're studying, what is the distance between the two stars, the average distance?
Yeah, good question. So I didn't really give you a sense of scale here. Each of so there's a unit that we often use in the solar system, and for this too, called the AU, or Astronomical Unit. So 1 AU is the distance from the Earth to the Sun, 93 million miles. So the scale of our solar system is maybe about 100 AU. So Pluto's 40 AU. Distant things in the Kuiper Belt beyond that go out to maybe 100 or a few hundred AU. The binaries that we're looking at here are anywhere from 300 AU to a few thousand AU apart. So like the scale of this disk that's over my shoulder here, the radius of that disk is maybe 100 AU. And the separation between these two is maybe 300 or 400 AU. We sort of have to study systems that are that wide or wider because those are the only ones where the disks survive. If the systems are closer to each other, the star messes up the disk and disrupts planet formation before it ever has a chance to happen.
That's what I was thinking. Yeah. Okay. Thank you.
Yep.
You also had a question in the chat. Mary asked a question. She asks, although our solar system is not a binary system, given that the planets orbiting the Kelt star are not in the same plane, would that indicate that Pluto could be promoted from a dwarf planet?
Got it. I see the question now. Great question.
Yeah.
I am certainly not going to take the bait and get back into the debate about whether Pluto should be a planet or not. But yes, I will. I would say no. And the reason for that is that what's the right way to say this? We understand Pluto a lot, but I would say the reason Pluto got shifted to a different status is that we understand it better than we used to. And in particular, that we see that it's not, that it, as one astronomer likes to say, Pluto found its friends, or we found Pluto's friends. It went from there's this great quote that I won't be able to reproduce exactly, but it said something like Pluto went from a freakish, isolated system to being part of a rich and interesting population in the solar system. And that's the rest of the Kuiper belt. And so we understand Pluto and its friends as the sort of larger leftovers of the planet formation process that sort of got cleared out and kicked into bigger orbits as planet formation was completing. And in particular, Pluto shares orbital characteristics with a bunch of other bodies that all have kind of a close approach to Neptune's orbit. So it was almost certainly, so some of you may be familiar with the fact that if you look at Pluto's orbit closely, there are times when it's actually closer to the sun than Neptune is, but only when they're on opposite sides of the sun. So there's a handful of these objects. That's sort of a signature of having gotten a kick from Neptune in the past into the orbit that it's in now. And so we think that's the reason that it has that tilt to it. And that's the reason that it's farther out there. So do you want to call it a planet or not? You can take your pick. I will say that this is going in a little bit different direction. If you haven't looked at the images from the New Horizons mission that had a close flyby from Pluto a few years ago, I had seen a handful of them in the press when it came out, but a year or so ago when I was teaching class, I went back and looked at it, and holy cow, it is really amazing to see, mountains and, all this detail. I mean, that really made me say, okay, Pluto's like a planet. I mean, you see these images, it shouldn't take, what we see on the surface shouldn't really determine whether it's a planet or not, but you certainly, I certainly saw it as more of a world, let me say it that way, than the whole time I was growing up, the best picture we ever had of Pluto was a fuzzy blob, right? You couldn't really see any detail on it. And it was the sort of last planet in the solar system, or last large object in the solar system, to have a close flyby and to see all that detail. So that's a bit of a different direction. But okay, other questions? If there's more in the chat there or not.
I think that's about it for questions.
Okay.
Great.
Well, again, really fun to be able to talk to everybody, and appreciate the chance to join your group.
Great. Thanks very much.
Thank you very much.
Yeah.
Thank you.
Take care.
Well, thanks everyone for joining us for the March meeting of the North Jersey Astronomical Group. For members, please do hang around. We are going to have a night sky presentation and a short meeting. And so, Mary Lou, could you remind us the speaker for next month for the April meeting?
Yeah, so April meeting is Wednesday, April 14th.
Right.
Michael Lewis from NASA Jet Propulsion Lab is going to talk about perseverance on Mars, what we've learned so far.
Great, cool.
It's down, it's working, so he has a topic.
Yeah.
Didn't blow up, so
Right.
we're going to hear something.
Right.